One important thing what we have learned about ferromagnetic materials is that they can be magnetized even after field is removed, and those materials which retain their magnetization are called hard magnetic materials, hard ferromagnets, and for which as soon as we remove the magnetic field, the magnetization goes off. Those materials are called soft ferromagnets. So the relation between this magnetic field and field intensity in ferromagnetic material is complex. So relation in B and H in ferromagnetic material is very complex. It is not a linear line and it depends on the magnetic history of the sample. So again there is a history of the sample. So now we are going to understand this curve. This is very important curve. This is called hysteresis curve. So this is called a hysteresis loop or hysteresis curve. So what happened? So this depicts the behavior of a material as we take it through one cycle of magnetization. So here one cycle of magnetization is shown. Let the material be unmagnetized initially. So initially the material is non-magnetized. So we start with this point. We start with this point. So what we are doing? Initially we are increasing the field intensity, and you know, so we have a solenoid, number of turns in this solenoid is n, number of turns per unit length. Now we fill this solenoid with some kind of material. Let us say this material is hard ferromagnet which will remain magnetized even after field removal. So now what is this field intensity? We know for solenoid without any material, this B0 or B0 is mu naught n I, and H is equal to B0 upon mu naught. That means I n, and I is in ampere, n is number of turns per unit length, length is in meter. So intensity is ampere per meter. So field intensity is ampere per meter. So we cannot change number of turns in the coil. What we can change? We can change the current. So more the current we supply, there will be more magnetic field because B is proportional to I. So more current we supply, so more the magnetic field in this solenoid, more current we supply. So if this field increase, the magnetization of the material will also increase, because that we have seen, if there is more field, the dipole will align in the same direction, more and more dipole will align in the same direction of the material. So now let us see what happens in that case. So we are increasing the field and we are seeing the effect on magnetism of the material. So we are observing how much this total magnetization. What is this total magnetization? Total magnetization is B naught plus Bm. So this B naught part is because of the solenoid, or that was initially there. This is because of this ferromagnetic material. So this is additional part. So this B combines both of them, and till now you know that this Bm, because of this material, this B becomes very high, 400 or 500 even 1000 times high. So this B naught is very small. Because of this Bm, this B becomes very high. So we are seeing that how this field affects this total magnetic field, that we are seeing. If we increase the field, what will happen to total magnetic field? Definitely it will increase, but how it will increase? So initially what we expected, that if we increase this field, magnetic field will increase. Again this field intensity is increased, magnetic field increase. So we thought that it must be a linear curve, but it is not a linear curve. So what is this curve? So let us see. So we are starting with this point and we are increasing the field intensity, that means current in the solenoid. We place it in a solenoid. So we have taken a material and placed it in a solenoid and increase the current. So we are increasing current through the solenoid. So current is increasing and material is inside the solenoid. The magnetic field B. So again see, this is total magnetic field. the field for the field already inside the solenoid plus field due to this material. In the material rises, so this field is also rising and saturated as depicts in the curve OA. So what is happening? So initially, as we increase the current in the solenoid, this magnetic field in the material also starts rising. So they are saying this is the field in the magnetic material. Also you know this B is equal to B0 plus Bm, okay, and you know this B0 is around 1, this is more than 1000, more than 1000. So we can remove this part, let us remove this part. So B is equal to Bm, B is nearly equal to Bm. So this is the field inside the material. We can say this is the field inside the material because most of the field is coming because of the material. So what will happen as we increase the field? So initially what will happen? The dipoles starts aligning and more dipole starts align and keep on aligning. But there comes a limit when all the dipoles align in a same direction. Now even if you increase the current but no more dipoles are there to align, so curve will become flat. Listen once again this thing. So what we are doing? We are increasing the field. So initially dipoles start aligning in a single direction. Now they start aligning. There comes a limit when all the dipoles are in single direction, same direction. Now whatever you increase current or not increase, all the dipoles are aligned in same direction. That means now no more magnetic field can be increased. Whatever you do, even if you supply 500 ampere per meter, still at that field intensity this dipole alignment will not increase or magnetic field will not increase. So this limit is called saturation limit. Saturation means this has become saturated. As you have learnt about saturated solutions that nothing more can be added. So similarly this thing has been saturated. Now no more dipoles can be aligned in the direction of the field because now all have aligned in the same direction. So there comes a saturation. So this is the saturation point. This behavior represents the alignment and merger of domains. So there is a merger of domains, that means all domains are in same direction until no further enhancement is possible. So there is no enhancement possible. It is pointless to increase the current. Now even if we increase the current, this will not change and hence the magnetic intensity H beyond this. So there is no point increasing magnetic intensity beyond this point. This is the maximum magnetic field that we can get. We cannot increase the magnetic field just by increasing H. Now next, now what will we do? So this is the point we have reached. So initially we took a material which was non-magnetized, we increase the field, we get this magnetic field which is at it as highest. So we have reached this point. Now what we are trying to do? Now we decrease H and reduce it to 0. So what we are doing? So now we are reducing H. We are reducing H. So as H is reduced, this is going on to this path. This is going to this path. At H is equal to 0, B is not equal to 0. So here we can see initially when the material was not magnetic, at H is equal to 0, there was no magnetic field. But once it has magnetized, so even at H is equal to 0, the material is still magnetic. The magnetic field is 1.2 Tesla. Why it is so? Because it is a hard ferromagnetic material. It has a memory. It remember that it was magnetized. Still definitely less number of dipoles aligned, but still a large number of dipoles are aligned in the same direction. Only few of them are in different direction. So even at 0 field there is some magnetic field. This is represented by the curve AB. So this is curve AB. Curve AB. The value of B at H is equal to 0 is called retentivity or remanence. So this is called retentivity or remanence. This comes in exam, that what is this point? called, this point is called retentivity, because the magnet was able to retain this much magnetization or this much was remaining there. So that's why it is called remanence or retentivity. Either you say that magnet or the material was able to retain, or you say that this was remaining magnetization, that means remanence. So this many times can be asked in your exams. In figure 5.14, in this figure Br is equal to 1.2 Tesla. So this remanent magnetization or remanence or retentivity is 1.2 Tesla, where the subscript R denotes the retentivity. So this is Br, retentivity or remanence magnetization. The domains are not completely randomized, so they are somehow they have reduced from full directional. So definitely they are all not in same direction, but now some of them are randomized. So definitely some decrease is there, but not completely zero, even though the external driving field is removed. So what is the sentence? The domains are not completely random even though external driving field is removed. So we have removed the external field, still all the domains are not completely random.